Hello there, and welcome to Sleepy Science Vault. You feel it right now. Sitting wherever you are, there is a force pressing you gently into your seat, holding the air around you close to the ground, keeping the oceans from drifting off into space. It asks nothing of you. It makes no sound. And yet it is one of the most profound and far-reaching forces in the entire universe. We call it gravity. And most of us never really think about it. Gravity is, at its heart, a force of attraction. Every object that has mass pulls on every other object that has mass. Not just planets and stars, everything. You are gravitationally attracting the chair beneath you, the walls around you, the moon above you. The effect is almost unmeasurably small at human scales, but it is real, and it is constant, and it never stops. Here on Earth, that attraction produces what physicists call a local gravitational acceleration of about 9.8 meters per second squared. What that means in plain language is this: if you drop something, anything, it will fall toward the ground, and with every passing second, it will be moving about 9.8 meters per second faster than it was the second before. A feather and a bowling ball, dropped together in a vacuum with no air resistance, would hit the ground at exactly the same moment. That idea still surprises people. But it's true. Now, what is it that actually generates gravity? What gives an object the ability to pull on everything around it? The answer is mass. Or more precisely, mass and energy, which at the deepest level of physics are really the same thing. Mass is gravity's currency. The more of it something contains, the stronger its gravitational presence. The Earth has an enormous amount of mass, which is why everything on its surface feels that steady, reliable pull downward. The Sun has far more mass still, which is why 8 planets trace long, looping paths around it across billions of kilometers of empty space. But here is something that might surprise you. Gravity, for all its grandeur, for all its ability to hold galaxies together, is extraordinarily weak. Compared to the other fundamental forces of nature, electromagnetism, and the forces that hold atomic nuclei together, gravity is almost laughably feeble. A small refrigerator magnet can hold a piece of paper against a wall, overcoming the gravitational pull of the entire planet Earth with nothing more than a thin strip of magnetized metal. The electromagnetic force between two electrons is roughly 10 to the power of 40 times stronger than the gravitational force between them. 40. That number is almost impossible to hold in your mind. And yet gravity wins, in the end, at the largest scales. Because it has one quality that the other forces do not. It always attracts. It never repels. And it reaches across infinite distance without ever fully switching off. Which brings us to something quietly remarkable about gravity: you cannot escape it locally. You cannot step outside of it. There is no room you can walk into, no material you can build a wall from, no technology that can create a bubble where gravity simply stops. Unlike electric charge, which can be neutralized, positive and negative canceling each other out, gravity has no opposite. There is no negative mass. There is nothing that falls upward. And so gravity cannot be shielded. If you built a hollow sphere of the densest material imaginable and climbed inside, you would feel no gravity from the shell itself, that much is true. But the earth beneath you would still pull you down. The moon above would still tug at you, gently and invisibly. Gravity passes through everything. Always. This quality is connected to something physicists call gravitational potential, a way of measuring not the force pulling on you right now, but the energy stored in your position. The higher you climb, the more gravitational potential energy you carry. That energy is what a falling object converts into speed on the way down. And it is this concept of potential, rather than raw force, that determines something even more dramatic: whether an object can ever escape a gravitational field entirely. The speed required to break free from a planet's gravity well is called escape velocity. On Earth, that speed is about 11.2 kilometers per second. Below that speed, whatever you throw will eventually curve back. Above it, the object can travel outward forever, slowing as it goes, but never quite stopped. The gravitational potential sets that threshold. It is the depth of the well you are trying to climb out of. And gravity sculpts the physical world in ways we rarely stop to notice. The reason planets are round is gravity. Over millions of years, a large enough mass of rock or gas will be pulled equally from all directions toward its own center, smoothing out its shape into a sphere. Gravity defines what we even mean by a surface, the boundary where the inward pull is strong enough to hold material in place against the chaos of impact, heat, and rotation. It also sets limits on how tall things can grow. On Earth, mountains can rise only so high before gravity wins. The rock at the base of a mountain is under immense pressure, the weight of everything above pressing down on it. At a certain height, that pressure becomes so extreme that the rock itself begins to flow, to deform, to sink. Mount Everest stands at roughly 8,800 meters. It is not the tallest that geometry allows, it is the tallest that gravity permits. Beyond that point, the crust simply cannot support the weight. The mountain would slowly collapse under itself. Gravity is patient that way. It does not rush. It does not force. It simply waits and pulls, and in the end, it always has the final word. There's a kind of invisible sorting happening in the air around you, right now, without any fanfare. The atmosphere you breathe is not a simple, uniform blanket of gas wrapped around the planet. It is a layered thing, organized quietly and continuously by gravity. Heavier molecules, the denser ones, carrying more mass, tend to drift lower, pulled more insistently toward the ground. Lighter gases, like hydrogen and helium, drift toward the upper edges of the atmosphere, where gravity's hold is weaker, and sometimes escape into space entirely. Nitrogen and oxygen, the gases that fill your lungs, settle into the comfortable middle layers, close enough to the surface for life to breathe, light enough to remain as a generous, life-sustaining envelope. This process is called gravitational settling. It happens in every atmosphere, on every planet with one. It is why the air near the ground is denser than the air at altitude, why your ears pop as you climb a mountain, why aircraft need pressurized cabins. Gravity, even in something as invisible as air, is always sorting, always organizing, always gently insisting on a particular kind of order. And here is something that sits right at the heart of how gravity behaves, something so fundamental that physicists have given it a name: the equivalence principle. Gravity acts on everything equally. Not equally in the sense that everything feels the same force. A more massive object does feel a stronger gravitational pull. But the acceleration produced by gravity is the same for every object, regardless of what it is made of, regardless of how much it weighs. Drop a marble and drop a cannonball from the same height, and they arrive together. This is not obvious. It should not, intuitively, be true. And yet every careful experiment ever performed has confirmed it, without exception. This was Galileo's great insight, likely demonstrated, at least in spirit, from a high tower in Pisa, though the famous story may be more legend than fact. And it was the thread that Newton would later pull on, and that Einstein would eventually follow all the way to a completely new understanding of what gravity actually is. But we will get to Einstein in time. For now, let us stay a little longer with the world as it feels, and with the quiet fact that gravity, even here on Earth, is not quite the same everywhere. The Earth is not a perfect sphere. It bulges slightly at the equator, pressed outward by the planet's rotation, and flattens at the poles. It has mountains and ocean trenches, dense regions of iron-rich rock and lighter areas of ancient granite. All of this means that gravity across the Earth's surface is subtly, measurably non-uniform. At the poles, you are slightly closer to the Earth's dense core, and the gravitational pull is fractionally stronger. At the equator, you are further from the center, and the outward push of the planet's spin slightly offsets the inward pull, making you fractionally lighter. The difference is small, only about 0.5% between the poles and the equator. But it is real, and sensitive instruments can measure it. Satellites now map these gravitational variations in extraordinary detail, and scientists use those maps to study ocean currents, to track the melting of ice sheets, to understand the hidden structure of the crust deep underground. Gravity, even in its slight unevenness, carries information. Underlying all of this, underlying every calculation, every orbit, every falling apple, is a single number. A constant. Physicists call it G, the gravitational constant, and it sets the fundamental strength of gravity throughout the universe. It appears in the equation Newton wrote to describe gravitational attraction. The force between two masses is equal to G multiplied by both masses, divided by the square of the distance between them. Change G, and you change everything. A larger G would mean stronger gravity, stars collapsing faster, planets forming more violently, life as we know it likely impossible. A smaller G, and matter might never have clumped together at all. What is striking is how difficult G has been to measure precisely. Unlike the speed of light, or the charge of an electron, which we now know to extraordinary precision, G remains one of the least precisely known constants in all of physics. The reason is that gravity between human-scale objects is so extraordinarily faint that measuring it requires painstaking care, near perfect isolation from vibration, temperature, and air currents, and experiments that can take months to run. Scientists have been refining the measurement of G for over 2 centuries, since Henry Cavendish first managed it in 1798 using 2 lead spheres and a delicate twisting wire. and we still do not know its value as precisely as we would like. There is something quietly humbling about that, the force that rules the cosmos, and we are still working out its exact strength. Now, let us follow the logic of gravity a little further. Let us follow the thread that Newton pulled. Newton's great contribution was not just the observation that gravity exists. It was the precise mathematical description of how it behaves, specifically, how it weakens with distance. His inverse square law states that gravitational force decreases with the square of the distance between two objects. Double the distance, and the force does not simply halve. It falls to 1/4 of what it was. Triple the distance, and it falls to 1/9. This relationship, so clean, so geometric, has profound consequences. Think about what it means in practice. If you could somehow stand on the surface of a planet twice as far from a star as the Earth is from the Sun, you would feel not half the gravitational pull of that star, but 1/4. The weakening is steep and swift. This is why the outer planets of our solar system move so much more slowly in their orbits than the inner ones. They are sitting in a shallower part of the gravitational slope, where the sun's pull is far gentler. And speaking of falling, there is a beautiful, counterintuitive truth buried in the way falling objects behave. When you hold an object and release it, it begins to fall. And as it falls, something is happening to the energy it carries. Up high, it has what physicists call gravitational potential energy, energy stored in its position, and how far it still has to fall. As it descends, that potential energy is continuously converted into kinetic energy, the energy of motion. The object moves faster and faster, trading height for speed, potential for movement, stillness for acceleration. By the time it reaches the ground, all of that stored potential has become motion. The crack of impact is just energy changing its final form one more time. This conversion, potential into kinetic, height into speed, is one of the most fundamental transactions in nature. It powers waterfalls. It drives the great ocean conveyor currents. It is the reason a ball rolls down a hill. Gravity is, in a sense, an enormous reservoir of stored energy, and the universe is always spending it. But perhaps the most elegant idea in all of gravitational physics, the one that changes how you see the night sky forever once you truly understand it, is this: orbits are not a special kind of motion. Orbits are falling. When the moon travels around the Earth, it is not being held up by some invisible string. It is falling. Constantly. Every second of every day, the moon is falling toward the Earth. What saves it from ever hitting us is that it is also moving sideways, fast enough that as it falls toward the Earth's surface, the surface itself curves away beneath it. The moon falls, and the Earth curves away, and the moon falls again, and the Earth curves away again, endlessly, in a perfect continuous loop. This was Newton's extraordinary insight. The moon and a falling apple are doing the same thing. Both are subject to the same gravitational force, described by the same equation. The only difference is sideways speed. An orbit is, at its core, a state of continuous freefall around a curved world. Astronauts aboard the International Space Station are not beyond Earth's gravity, they are very much within it. They feel weightless not because gravity has disappeared, but because they are falling, together with their spacecraft, in a continuous arc around the planet. Everything around them is falling at the same rate, and so there is no surface pushing up on their feet, no sense of weight, no up or down. Weightlessness is not the absence of gravity. It is the experience of falling freely inside it. And if you fall fast enough, you never come back. Escape velocity, the speed required to break free from a gravitational field entirely, is determined by how deep that gravitational well is. On Earth, as we touched on before, that speed is about 11.2 kilometers per second. But escape velocity is not a force you fight continuously, it is a threshold. Reach that speed at the surface, point yourself outward, and you will travel forever away from Earth, slowing gradually but never quite stopping, never quite falling back. For a more massive planet, the well is deeper, and the escape velocity higher. For a neutron star, one of the densest objects in the known universe, the escape velocity is a significant fraction of the speed of light. And for a black hole, the escape velocity at a certain boundary exceeds the speed of light entirely. Nothing, not even light itself, can fall fast enough to climb back out. But that is a story for another part of this journey. For now, sit with the quiet elegance of what Newton gave us, a single equation, a single relationship between mass and distance, that describes the falling apple, the orbiting moon, the path of every planet, the shape of every comet's long elliptical arc across the sky. He found the grammar of gravity. And the universe, it turned out, had been speaking it all along. Every satellite you have ever used, every GPS signal that has guided you through an unfamiliar city, every weather image downloaded from orbit, every phone call bounced through space and back, exists because of a carefully maintained act of perpetual falling. Satellites do not hover. They are not held up. They are, at every moment, in the same condition as Newton's moon, dropping toward Earth under the full force of gravity, while simultaneously moving sideways fast enough that the planet's surface keeps curving away beneath them. The altitude of an orbit determines the speed required to maintain it. Low Earth orbit satellites, the ones that race across the sky in roughly 90 minutes, must travel at about 7.8 kilometers per second to keep from spiraling inward. Higher up, where the gravitational pull is weaker, the required speed is lower, and orbits take longer to complete. The International Space Station completes 16 orbits of Earth every single day. 16 times, every day, it traces the same elegant falling arc around a planet whose gravity it will never escape. And when we want to send spacecraft not just around Earth but out into the deeper solar system, we use gravity itself as an engine. Gravitational slingshots, more formally called gravity assists, are one of the most ingenious techniques in the history of spaceflight. The principle is this: a spacecraft approaches a planet, swings around it in a carefully calculated arc, and departs on a new trajectory, moving faster than when it arrived. Energy is transferred from the planet's own orbital motion around the Sun into the spacecraft. The planet loses an infinitesimally tiny amount of speed, completely unmeasurable in practice, and the spacecraft gains enough to reach destinations that would otherwise require impossible amounts of fuel. Voyager 1, launched in 1977, used gravitational slingshots around Jupiter and Saturn to accelerate outward. It is now the most distant human-made object ever built, traveling through interstellar space, more than 23 billion kilometers from the Sun. It got there largely on borrowed gravity. There is something almost poetic about that. We did not push our way out of the solar system. We borrowed momentum from the giants, and they let us go. Now, here is something that might seem obvious once stated, but is worth pausing to truly absorb. Gravity has no off switch, and it has no edge. The gravitational influence of every object in the universe extends outward in all directions, forever. It weakens with distance, rapidly, as we have seen, but it never reaches zero. The Sun's gravity reaches Neptune. It reaches Pluto, and the distant Oort cloud, and technically speaking it reaches every corner of the observable universe, though at those scales its influence is so faint as to be practically invisible. You are gravitationally connected, right now, to the Andromeda Galaxy, to stars you will never see, to matter scattered across distances so vast they have no meaning in human experience. The connection is real. The attraction is real. It is simply overwhelmed by everything else happening at those scales. And when something changes, when a star explodes, when two black holes collide, when any mass anywhere is accelerated, that change in the gravitational field does not propagate instantly. It travels. It spreads outward like a ripple in a pond, moving at exactly the speed of light. This was one of the predictions of Einstein's general theory of relativity, and for decades it was untested, because detecting such ripples seemed almost impossibly difficult. In 2015, it was confirmed. Two black holes, each roughly 30 times the mass of our Sun, spiraling toward each other across more than 1 billion light-years of space, merged in a fraction of a second. The gravitational waves they produced, distortions in the very fabric of spacetime, washed across the universe at the speed of light, and finally reached Earth, where instruments sensitive enough to detect a change in length 1/10,000th the diameter of a proton registered their arrival. The signal lasted less than a second. It had been traveling for over 1 billion years. We felt gravity change. We heard, in a sense, the universe move. This matters beyond the wonder of it. It confirms that gravity is not an instantaneous force reaching across space in defiance of physics. If the Sun were to suddenly vanish, which it cannot, but as a thought experiment, Earth would not immediately fly off into darkness. For approximately 8 minutes, we would continue orbiting as normal, because that is how long it takes light, and gravitational influence, to travel from the Sun to us. We exist in a gravitational field that is always, slightly, out of date. And gravity's reach across enormous distances does something else quietly remarkable. It links objects that are nowhere near each other into long, patient relationships. Consider the tides. Most people know that the moon causes tides. But the mechanism is worth understanding slowly, because it reveals something deeper about how gravity behaves across extended objects. The moon does not simply pull the Earth toward it. It pulls different parts of the Earth by different amounts. The side of Earth closest to the moon is pulled more strongly. The center of Earth is pulled a little less. the far side is pulled less still. This difference in gravitational pull across the body of the Earth, this gradient, is what creates tidal forces. The water on the near side of Earth is pulled toward the Moon slightly more than the solid Earth beneath it, so it bulges outward. The water on the far side is pulled toward the Moon slightly less than the solid Earth, so relative to the planet, it too bulges outward, in the opposite direction. This is why there are 2 high tides per day as Earth rotates beneath these 2 bulges, one on the side facing the Moon, one on the side facing away. The Sun also contributes to Earth's tides, despite being so much farther away. When the Sun and Moon align, at new moon and full moon, their tidal forces combine, producing the dramatic spring tides. When they are at right angles, they partially cancel, producing the gentler neap tides. The ocean is, in a very real sense, a clock, keeping time with the positions of the Moon and Sun. But tidal forces do not only move water. They deform solid objects too. The solid Earth itself flexes under tidal stress, rising and falling by roughly 30 centimeters twice a day. You cannot feel it. Your body is too small, and the deformation is spread across the entire planet. But it is real, and it is measurable. Rock, given enough force applied slowly enough over a large enough scale, yields like everything else. On smaller and denser bodies, moons orbiting close to massive planets, this tidal flexing becomes something extraordinary. Io, one of Jupiter's 4 large moons, is the most volcanically active body in the entire solar system. Its surface is covered in sulfur plains, lava lakes, and erupting volcanoes that hurl material hundreds of kilometers into space. And the reason is tides. Io orbits so close to Jupiter, and Jupiter is so enormously massive, that the tidal forces squeezing and releasing Io as it moves slightly closer and further in its orbit generate enough internal friction to melt rock. The Moon is being heated from the inside out by nothing more than the unequal pull of gravity. Europa, another of Jupiter's moons, may have a liquid water ocean beneath its icy surface, kept liquid, scientists believe, by the same tidal heating mechanism. It is one of the most compelling candidates in the solar system for the possibility of life. And if life exists there, it will owe its existence, in a strange and indirect way, to the differential pull of a giant planet's gravity. Now, in a solar system full of orbiting bodies, all pulling on each other, all influenced by each other's gravity across vast distances, you might expect chaos. You might expect orbits to slowly drift and destabilize, for moons to wander, for planets to occasionally nudge each other into catastrophic paths. Sometimes that does happen. But often, something else occurs instead, something called gravitational resonance. When 2 orbiting bodies have orbital periods that form a simple ratio, 2 to 1, 3 to 2, 4 to 3, their gravitational interactions repeat in a regular, predictable pattern, and over time, those interactions reinforce each other in a stabilizing way. The orbits lock together like gears, each one reinforcing the other's regularity. Io, Europa, and Ganymede, 3 of Jupiter's moons, are locked in a precise resonance. For every 1 orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This Laplace resonance, as it is called, has persisted for billions of years and keeps the moon's orbit stable and predictable. It is gravity turned into a kind of clockwork, worlds keeping time with each other across the void. Resonances are found throughout the solar system. Pluto and Neptune are in a 3-to-2 resonance, which is actually what keeps them from ever colliding despite their orbits crossing on paper. Many of the gaps in Saturn's rings, those clean, dark bands where ring particles are notably absent, are carved out by resonances with Saturn's moons, which repeatedly sweep those regions clear. Gravity, at these scales, is not just a force pulling things together. It is a choreographer, arranging motion into patterns, locking cycles into ratios, turning what could be chaos into something that looks, from a distance, like order. And then there are binary stars, pairs of stars in orbit around each other, so common in the galaxy that astronomers now believe more than half of all sun-like stars have at least one stellar companion. In these systems, gravity shapes everything. The stars' relative masses determine the size and shape of each orbit. If they are close enough, tidal forces stretch each star slightly toward the other. If they are close enough still, material can flow from one star to the other along streams of gas, building accretion disks, altering the chemistry and lifespan of both. Some binary systems are so tightly locked that both stars have become tidally distorted into elongated egg shapes, each permanently facing the other as they spin. Others are so wide that they take thousands of years to complete a single shared orbit, each star barely aware of the other's presence, drawn together only by the faintest gravitational thread. In the most dramatic cases, one star dies first, collapsing into a neutron star or black hole, and continues to feed on its companion, slowly devouring it across millions of years. These are among the most energetic and violent environments in the known universe, and they exist because two stars, long ago, ended up close enough that gravity refused to let either of them simply go. Gravity, even across the enormity of the cosmos, is patient. It builds slowly. It locks things into rhythms. It links distant objects into relationships that last for billions of years, shaping the fates of moons and stars and oceans and everything in between. And we are only just beginning to understand the full depth of what it does. For most of human history, gravity was understood as a pull, an attraction, a force reaching invisibly across space, drawing things together. Newton gave us the mathematics to describe it with extraordinary precision, and for more than 2 centuries, those mathematics were enough. They predicted planetary positions. They guided spacecraft. They described the fall of every apple from every tree. But Newton himself was never fully satisfied. He knew his equations described gravity beautifully. He did not know what gravity actually was. "I feign no hypotheses," he wrote, famously. The mechanism remained a mystery, and he left it that way. It took another 200 years, and a mind unlike any other, to look at that mystery and find the answer waiting inside it. But before we arrive at Einstein, let us spend a little time with gravity as it operates dynamically, capturing, shearing, destabilizing, clustering, because the story of what gravity does in practice is rich enough to carry us a long way. When a body moves through space and passes close enough to a more massive object, something remarkable can happen. Rather than continuing on its original path, the smaller body loses enough energy, through gravitational interaction, or through collisions with gas and dust in the vicinity, to become gravitationally bound. Its trajectory curves inward, loops back, and settles into an orbit. Gravity has captured it. This is how many moons in our solar system likely arrived. The outer moons of Jupiter and Saturn, those irregular, distant, oddly inclined moons that do not fit the tidy pattern of the inner ones, are almost certainly captured objects. Asteroids, or perhaps fragments from early collisions, that wandered too close and never left. Mars's two small moons, Phobos and Deimos, may share a similar origin. Even our own moon, though its story is more dramatic, likely born from a colossal impact early in Earth's history, was shaped and held by the same gravitational logic. Capture is not gentle. It requires the right speed, the right angle, the right amount of energy dissipation at the right moment. But given billions of years and billions of objects moving through a gravitational landscape, capture happens, again and again, gradually assembling the layered, complex architecture of planetary systems. In rotating systems, disks of gas and dust around young stars, the flat spiraling arms of galaxies, gravity produces something called gravitational shear. Because different parts of a rotating disk orbit at different speeds, material at different distances from the center pulls gradually apart, stretched by the difference in orbital velocity. Inner regions orbit faster, outer regions more slowly, and the disk is continuously being pulled in slightly different directions at every point along its extent. This shearing is not purely destructive. It shapes the structures that form within disks. It influences where gas clumps, where density waves propagate, where rings form and where they break apart. In the great spiral arms of galaxies, gravitational shear is partly responsible for maintaining the sweeping curved shape, as stars and gas clouds move through regions of higher and lower density, the arms themselves persisting as waves rather than fixed structures. Closely related to this is differential rotation, the phenomenon where different latitudes or radii of a rotating body complete their rotations at different rates. The Sun rotates faster at its equator than at its poles. The gas giants do the same. In these environments, gravity works together with pressure and rotation to maintain these complex, layered flow patterns, each region following its own dynamical path while remaining part of a larger coherent whole. But for all gravity's capacity to organize and stabilize, it also harbors a subtler capacity, the ability to destabilize. In any system of three or more gravitating bodies, the interactions quickly become too complex for simple, closed solutions. Small perturbations, a slight nudge from a passing object, a gradual shift in orbital parameters, can be amplified over time, especially near what dynamicists call resonance zones, where gravitational interactions repeat in a reinforcing pattern. Rather than stabilizing the orbit, as we saw earlier with Io and Europa, certain resonance configurations can act as a pump, slowly injecting energy into an orbit until it becomes irregular, elliptical, or ultimately unstable. This is why certain regions of the solar system are largely empty. The Kirkwood gaps in the asteroid belt are carved not just by simple resonance locking but by chaotic zones, regions where Jupiter's gravitational influence has, over millions of years, excited the orbits of any asteroids that wander there, sending them onto crossing paths with Mars or the inner planets, eventually ejecting them entirely. Chaos, in the mathematical sense, does not mean random. It means exquisitely sensitive to initial conditions. A tiny difference in starting position or velocity, amplified through repeated gravitational interactions, can produce wildly different long-term outcomes. Some orbits in the outer solar system are chaotic on timescales of millions of years. Even the orbits of the inner planets, including Earth's, show traces of this sensitivity when modeled across hundreds of millions of years. The solar system is stable for now, but it is not, strictly speaking, perfectly stable forever. And yet, despite all this complexity, despite resonances and sheer and chaotic zones, when you step back and look at the largest scales, gravity reveals one of its most consistent behaviors: it clusters. Matter attracts matter. Clumps grow. Small overdensities in the early universe, regions that were only fractionally denser than their surroundings, slowly pulled in more material, growing denser still, attracting more, growing further. Over hundreds of millions of years, this process built the cosmic web, vast filaments of galaxies stretching across the universe, separated by enormous near-empty voids, intersecting at dense nodes where galaxy clusters accumulate. Galaxies cluster into groups. Groups cluster into clusters. Clusters gather into superclusters. The hierarchy goes upward in scale almost as far as we can see. At every level, gravity is the architect, patiently building structure from structure, linking the small into the large across incomprehensible spans of time and distance. At the other end of this hierarchy, gravity also defines the outer limits of planetary systems, the boundary beyond which the sun's influence can no longer reliably hold objects in bound orbits. This boundary, sometimes called the Hill sphere or the gravitational sphere of influence, marks the edge of our solar family. Beyond it, the gravitational pull of other stars, and the slow drift of the galactic tide, can gradually unravel loosely bound orbits. Objects in the outer Oort clouds sit near this boundary, held by the thinnest of gravitational threads, occasionally nudged inward by a passing star to become the long-period comets that sweep through the inner solar system every few thousand years. So gravity captures, and shears, and occasionally destabilizes, and builds hierarchies, and defines borders. It is dynamic and complex and subtle in ways that took centuries of mathematics to begin untangling. And then came a young patent clerk in Bern, Switzerland, who looked at all of this and suggested that we had been thinking about it wrong from the very beginning. Not wrong in the sense of inaccurate. Newton's equations still work, still predict, still guide spacecraft with exquisite precision. Wrong in the deeper sense. Wrong about what gravity fundamentally is. Albert Einstein spent years troubled by a deceptively simple question. Newton's law of gravity described a force that acted instantaneously across any distance. But Einstein's special theory of relativity, published in 1905, had established that nothing, no information, no signal, no influence, could travel faster than light. These two ideas could not both be true. Something had to give. The answer Einstein found, after a decade of some of the most difficult thinking in the history of science, was this: gravity is not a force at all. Gravity is the curvature of space-time. Let that settle for a moment, because it requires a genuine shift in how you picture the world. Newton had imagined space as a flat, fixed stage on which matter moves, and gravity as an invisible force acting between actors on that stage. Einstein dissolved the stage itself. In general relativity, space and time are not a passive background. They are a dynamic, flexible fabric, four-dimensional space-time, and mass and energy warp that fabric, curving it, bending it, shaping it in their vicinity. Imagine placing a heavy ball on a stretched rubber sheet. The sheet curves downward around the ball, creating a depression, a well. A smaller ball rolling across the sheet will curve toward the larger one, not because any force is pulling it sideways, but because the sheet itself is curved and the ball is simply following the shape of the surface. This is an imperfect analogy. It works in two dimensions and requires the concept of gravity to explain the rolling in the first place, but it captures something of the essential geometry. In Einstein's picture, objects moving through spacetime do not experience a force pulling them off a straight path. They are traveling in a straight line, the straightest line possible through a curved geometry. These paths are called geodesics, and in the presence of mass, geodesics curve. The Earth does not orbit the Sun because the Sun is pulling it. The Earth follows the straightest possible path through the curved spacetime the Sun has created around itself. What we perceive as gravitational attraction is simply the geometry of the local spacetime insisting on a particular path. This is a profound and deeply strange idea. But it makes predictions that Newton's theory does not, and those predictions have been confirmed, again and again, with increasing precision, for more than a century. The orbit of Mercury, for instance, drifts slowly around the Sun, a phenomenon called the precession of the perihelion, in a way that Newton's equations could not quite explain. The discrepancy was small but persistent, and it had puzzled astronomers for decades. Einstein's equations predicted it exactly, with no adjustments needed. Light, passing close to a massive object, follows a geodesic through curved spacetime, and since spacetime itself is curved, the light bends. Astronomers observed this during a solar eclipse in 1919, watching distant stars appear to shift their positions as their light grazed the Sun's warped spacetime on the way to Earth. The measured shift matched Einstein's prediction precisely. It was the moment the world realized something fundamental had changed in how we understand the universe. Gravity, in this new picture, is not a force transmitted between objects. It is geometry. It is the shape of the space and time that everything moves through. Mass tells spacetime how to curve, and curved spacetime tells mass how to move, a mutual, continuous conversation written in the language of differential geometry. Newton gave us the rules. Einstein gave us the reason. And the reason turned out to be more beautiful and stranger than anyone had imagined. One of the things that makes Einstein's general relativity so different from everything that came before it is that it does not separate two questions that Newton's framework had always treated independently. In classical mechanics, you first calculate the gravitational field, and then you calculate how objects move within it. 2 steps. two separate problems. In general relativity, these two things cannot be pulled apart. The distribution of mass and energy determines the curvature of spacetime. That curvature determines how mass and energy move. And how they move changes their distribution. And that changes the curvature. It is a single, continuous, self-consistent problem, and Einstein's field equations solve for both at once, the geometry of spacetime and the motion of everything within it, simultaneously, as one inseparable whole. This is part of what makes general relativity so mathematically demanding. You cannot simply calculate the stage and then choreograph the dance. The stage changes as the dancers move, and the dancers move differently because the stage is changing. Everything is coupled. Everything responds to everything else. And what, precisely, creates the curvature? What is it that bends spacetime? The answer, in general relativity, is broader and more surprising than simply mass. Einstein's equations respond to what physicists call the stress-energy tensor, a mathematical object that encodes not just the density of mass and energy in a region of space, but also momentum, pressure, stress, and the flow of energy in every direction. Spacetime does not curve only in response to matter sitting still. It curves in response to everything that carries energy or exerts pressure. This has consequences that feel almost counterintuitive at first. Pressure, by itself, contributes to gravity. In ordinary situations, stars, planets, everyday objects, this contribution is completely negligible compared to the mass-energy term. But inside a neutron star, where pressures reach magnitudes beyond anything achievable in a laboratory, pressure becomes a meaningful source of spacetime curvature in its own right. More gravity means more pressure required to resist collapse. More pressure means more gravity. In extreme cases, this feedback loop contributes to the eventual collapse of the most massive neutron stars into black holes, gravity, in a sense, helping to create the very conditions that overwhelm resistance to it. Radiation, too, pure energy moving at the speed of light, curves spacetime. In the very early universe, when temperatures were so extreme that radiation dominated the energy content of the cosmos, it was radiation that primarily drove the expansion and curvature of spacetime on the largest scales. The universe was not only full of matter. It was full of gravity generated by light itself. There is another quality of general relativistic gravity that makes it unlike any other force in physics: it is nonlinear. It interacts with itself. In electromagnetism, the electromagnetic field carries no electric charge, so it does not create more electromagnetism by its own existence. Gravitational fields, however, carry energy. And energy, in general relativity, is a source of gravity. So a gravitational field generates more gravitational field. The equations that describe this are extraordinarily complex, because the source of gravity is itself gravitational, creating a recursive, self-referential structure that has no counterpart anywhere else in classical physics. In most situations we encounter, this nonlinearity is completely undetectable. The gravitational field of the Earth is so weak, by relativistic standards, that the self-interaction of gravity contributes almost nothing measurable. But around the most compact and massive objects, neutron stars, black holes, the nonlinearity becomes essential. It is part of what makes those environments so mathematically rich and so difficult to fully describe. Now, here is one of the most elegant and humanly relatable ideas in all of general relativity. Something you can almost feel. Einstein realized early in his thinking that a person in free fall, someone falling freely under gravity, with nothing supporting them, would feel no gravity at all. If you stepped off a building and fell freely, ignoring air resistance, you would feel weightless. Every part of your body would be accelerating at the same rate. There would be no surface pushing up on your feet, no differential force across your body. In that falling frame of reference, locally, gravity would seem to have vanished. Einstein called this the happiest thought of his life. It meant that gravity and acceleration are, locally, indistinguishable. A person in a sealed box, accelerating upward in empty space at 9.8 meters per second squared, would feel exactly the same as a person standing still on Earth's surface. There is no local experiment they could perform to tell the difference. This equivalence, deep, exact, and universal, was one of the foundation stones on which general relativity was built. And it means that free fall is, in the language of general relativity, the natural, unforced state of motion. It is not falling that requires explanation. It is standing still on the ground, being pushed upward by the surface beneath you, constantly accelerated away from the free fall path, that represents the deviation. The ground is pushing you. Gravity, in this picture, is not pulling you down. The floor is pushing you up. It is one of those ideas that, once you sit with it long enough, quietly rewires something in how you experience your own weight. Now, if gravity is the curvature of spacetime, what happens when the source of that curvature is not just sitting still, but spinning? A rotating mass does something that a stationary mass does not. It does not merely curve spacetime around itself, it drags it. As a massive body rotates, it pulls the fabric of spacetime along with it, the way a spinning ball submerged in honey would drag the honey in slow circular motion around it. This effect is called frame dragging, or the lens stirring effect after the physicists who first described it mathematically in 1918. Frame dragging is extraordinarily subtle near ordinary objects. Around the Earth, the effect is real but so small that measuring it required decades of technological development. Satellites carry their own reference frames, their own local sense of direction, as they orbit, and frame dragging causes those reference frames to slowly precess, to twist, over the course of many orbits. The effect, for a low Earth orbit, amounts to roughly 40 milliarcseconds per year. A vanishingly small angle. But real. The Gravity Probe B mission, launched by NASA in 2004, was designed specifically to measure this effect. For extraordinarily precise gyroscopes, cooled to near absolute zero, were carried in a satellite orbiting Earth for more than a year. The drift in their orientation, accumulated over thousands of orbits, matched general relativity's predictions to within a small margin of error. We had measured spacetime being dragged by a spinning planet. Around black holes, frame dragging becomes not a subtle correction but a dominant feature of the environment. close to a rapidly spinning black hole, spacetime itself rotates. There is a region around it, the ergosphere, within which nothing can remain stationary relative to distant observers, no matter how powerful its engines. Spacetime is moving, and everything within it moves with it, whether it chooses to or not. General relativity also predicted what happens to gravity's influence on light and on the flow of time, and both predictions were, again, confirmed by experiment. We have already seen that light bends around massive objects, following curved geodesics through warped spacetime. But gravity also changes the frequency of light, its color. A photon climbing out of a gravitational well expends energy doing so. It cannot slow down. Light always travels at the same speed, but it loses energy in another way. Its frequency decreases. Its wavelength stretches. Light that began its journey as blue, high-frequency radiation shifts toward the red end of the spectrum as it climbs away from a massive body. This is gravitational redshift. The opposite also occurs. Light falling deeper into a gravitational well gains energy, its frequency increasing, shifting toward the blue. On Earth, this effect is small but measurable. Pound and Rebka demonstrated it experimentally in 1959, by measuring the shift in gamma-ray frequency between the top and bottom of a tower at Harvard, a height difference of just 22.5 meters. The result matched relativity's prediction to within 10%. Later experiments refined it to 1%, and eventually better still. Gravitational redshift has real, practical consequences. The GPS satellites orbiting Earth are at higher altitude than the ground, where gravity is slightly weaker and time runs fractionally faster. If this were not accounted for, GPS positioning errors would accumulate at roughly 10 kilometers per day, rendering the entire system useless. Every time you use navigation on your phone, a correction derived from general relativity is quietly operating in the background, keeping your position accurate. Einstein's equations are not abstract curiosities. They are embedded in the technology of everyday life. And Mercury. Let us return, briefly, to Mercury, because its orbit carries a kind of historical weight. Astronomers in the 19th century had noticed that Mercury's orbit was behaving oddly. The point at which Mercury passes closest to the Sun, its perihelion, was slowly rotating around the Sun over time, tracing out a rosette pattern rather than a fixed ellipse. Most of this precession could be explained by the gravitational influences of the other planets. But a small residual, 43 arcseconds per century, remains stubbornly unaccounted for. Various explanations were proposed. A hidden planet closer to the Sun, never found. Corrections to Newton's law, never satisfactorily justified. When Einstein completed his general theory of relativity in 1915 and applied it to Mercury's orbit, the 43 arcseconds emerged from the mathematics exactly, with no adjustment, no additional hypotheses, no free parameters. The calculation matched the observed anomaly precisely. For Einstein, this was the moment he knew the theory was right. He later said the discovery gave him palpitations of the heart. A century of unexplained astronomical data, dissolved by a new understanding of what space and time actually are. General relativity is now one of the most precisely tested theories in all of science. It has been confirmed by binary pulsars, by the expansion of the universe, by gravitational lensing, by the detection of gravitational waves, by the shadow of a black hole imaged for the first time in 2019. Every test has returned the same answer: the equations are right. And at the center of all of it is this single, extraordinary idea that what we experience as gravity is the universe's geometry in motion. Mass curves spacetime. Spacetime guides mass. Pressure gravitates. Light bends and redshifts. Time runs differently depending on where you stand. Spinning objects drag the very fabric of reality around them. Newton gave us the power to predict the universe. Einstein gave us the language to understand it. And yet the story is not finished. Because there are places where even general relativity goes quiet, where the equations reach their limits, where a deeper theory must be waiting. We have not found it yet. But we are listening. Time does not pass at the same rate everywhere. This is not a metaphor. It is not a poetic way of saying that time feels different depending on your mood or your circumstances. It is a physical fact, confirmed by experiment, built into the structure of the universe at the deepest level we can access. Clocks run slower in stronger gravitational fields. The closer you are to a massive object, the deeper you sit in its gravitational well, the more slowly time passes for you, relative to someone farther away. This is gravitational time dilation, and like so many of relativity's predictions, it sounds like science fiction until you realize it has been measured in a laboratory, confirmed by atomic clocks flown on aircraft, and quietly accounted for in technology you use every single day. The effect on Earth's surface is small. If you spent your entire life at sea level rather than on a mountain, you would age a few microseconds more than someone who lived at high altitude. The difference is real but biologically meaningless for human experience. For precise instruments, however, it matters enormously. The GPS satellites that orbit Earth are approximately 20,000 kilometers above the surface, where Earth's gravitational field is weaker. Time up there runs faster than it does on the ground, by about 45 microseconds per day due to the weaker gravity, partially offset by about 7 microseconds per day from the time dilation caused by the satellite's orbital speed. The net result is that satellite clocks run roughly 38 microseconds fast per day compared to clocks on the ground. 38 microseconds sounds trivial. But GPS works by measuring the precise travel time of radio signals between satellites and receivers. The speed of light is approximately 30 centimeters per nanosecond. An uncorrected error of 38 microseconds, 38,000 nanoseconds, would translate into a positional error of more than 10 kilometers, compounding every single day. The system would be useless within hours. Every GPS receiver, every navigation app, every precision timing system that depends on satellite signals incorporates a correction derived directly from Einstein's equations. General relativity is not background theory. It is active engineering. And time dilation is only one consequence of curved spacetime. Light, too, is affected, in ways that have opened an entirely new branch of astronomy. We established earlier that light follows geodesics, the straightest possible paths through curved spacetime. Near a massive object, those paths curve. Light bends. And when the object is massive enough, and the geometry is right, this bending becomes not just a measurable deflection but a lens. Gravitational lensing occurs when a massive foreground object, a galaxy, a cluster of galaxies, or even a single compact star, sits between us and a more distant source of light. The mass warps spacetime around it, and light from the distant source curves around the intervening mass from multiple directions, converging toward the observer. The result can be multiple images of the same background object, arcs of distorted light stretched around the lensing mass, or in perfect alignment, a complete ring of light, an Einstein ring, encircling the foreground object. These are among the most visually striking phenomena in the observable universe. Deep field images from space telescopes show galaxy clusters surrounded by long, curved arcs of blue and white, the distorted images of galaxies far behind them, their light bent and magnified by hundreds of billions of solar masses of intervening matter. But gravitational lensing does something more profound than produce beautiful images. It reveals mass that cannot be seen. When astronomers calculate how much a galaxy cluster should bend the light passing around it, based on the visible matter, stars, gas, dust, the numbers do not match. The lensing is consistently stronger than visible matter alone can explain. Something else is there, something with mass, something that curves spacetime and bends light, but emits nothing we can detect. No light, no radio waves, no X-rays. Nothing. This is one of the most compelling lines of evidence for dark matter, the invisible, unidentified substance that appears to make up roughly 85% of all matter in the universe. We cannot see it. We cannot touch it. We know it primarily because of what it does to light, through the geometry of spacetime that general relativity gave us the tools to read. Gravitational lensing has effectively allowed us to map the distribution of invisible mass across the cosmos, tracing the architecture of something we cannot directly observe, using only the bending of ancient light as our instrument. And the lensing effect produces one more remarkable phenomenon, strange enough to pause over. When light from a distant quasar travels to us along multiple paths bent around a lensing galaxy, those paths are not identical in length. One route may be fractionally longer than another, passing through slightly different regions of curved spacetime. The same event, a flare in the quasar, a sudden brightening, will arrive at Earth along each path at slightly different times. The delay between these echoes can range from days to years, depending on the geometry. Astronomers have observed this effect directly. They watch a quasar brighten, then wait, sometimes months, sometimes longer, and see the same brightening appear again in a second image of the same quasar, the light having traveled a longer path around the same intervening mass. The same moment in cosmic history, arriving twice. There is something quietly astonishing about that. A single flash of light from billions of years ago, split by gravity, traveling two different roads through curved spacetime, arriving at our telescopes at different times. The universe holding its own echo. But all of this, time dilation, gravitational redshift, lensing, frame dragging, represents gravity in conditions we might still call moderate. Extreme by everyday standards, but not at the limit. For the limit, we must go somewhere that general relativity itself predicted but that many physicists, including Einstein at various points, found too strange to fully accept. We must talk about black holes. A black hole forms when matter is compressed beyond a critical threshold, when gravity overwhelms every other force that might resist it. In a massive star at the end of its life, the outward pressure of nuclear fusion has, for millions of years, balanced the inward pull of the star's own gravity. When the fuel runs out and fusion stops, that balance collapses. The core falls inward, and if it is massive enough, more than roughly 3 times the mass of our Sun, nothing stops it. Not electron degeneracy pressure, as in white dwarfs. Not neutron degeneracy pressure, as in neutron stars. The collapse continues until the mathematics reaches a singularity, a point where density becomes formally infinite and the known laws of physics cease to give meaningful answers. Around this collapsed core, at a specific distance determined by its mass, lies a boundary. A surface of no return. The event horizon. At the event horizon, the escape velocity equals the speed of light. Inside it, the escape velocity exceeds the speed of light. And since nothing, no matter, no radiation, no information of any kind, can travel faster than light, nothing that crosses the event horizon can ever get back out. Not a rocket. Not a radio signal. Not a single photon. The event horizon is not a physical surface. There is no wall there, no solid boundary you would feel as you crossed it. An astronaut falling freely into a sufficiently massive black hole might cross the horizon without any immediate sensation, with nothing locally to mark the moment of passage. The tragedy is not the crossing. The tragedy is what comes after, the inevitable continuation of the fall toward the singularity, with no possibility of return, no way to signal the outside universe, no escape regardless of what is done next. From outside the black hole, however, the view of that falling astronaut tells a completely different story, and one that illustrates gravitational time dilation taken to its ultimate extreme. As an object falls toward the event horizon, it moves into a region of increasingly intense gravitational time dilation. From the perspective of a distant observer, the falling object's clock runs slower and slower, its motion appears to decelerate, and it seems to asymptotically approach the horizon without ever quite reaching it. The light from the falling object is increasingly redshifted, stretched toward longer and longer wavelengths, and the object appears to dim and fade, frozen in the act of crossing a threshold it never, from the outside view, quite reaches. This apparent freezing is an observational effect, not a physical one. The infalling object does cross the horizon, and does so in finite proper time, its own time, as measured by its own clock. But the light carrying that information away from the horizon is so strongly redshifted that it never effectively escapes. The final moments before the crossing are, to outside observers, stretched toward eternity. Light emitted just outside the event horizon is redshifted to an extraordinary degree. Frequencies drop, wavelengths stretch, until what began as visible light becomes radio waves, then wavelengths too long to detect. A black hole, observed from outside, is effectively dark, not because nothing exists there, but because the gravity is so extreme that light cannot carry information outward with any useful energy. And then there are the spinning ones. Most black holes formed from collapsing stars will rotate, because the stars they came from were rotating. And a rotating black hole is a fundamentally different object from a simple, stationary one. Its geometry is not spherically symmetric. Around it, spacetime does not merely curve, it swirls. It rotates with the black hole, and this frame-dragging effect, which we measured so delicately around the Earth, becomes near a rapidly spinning black hole a dominant and inescapable feature of the geometry. The region where frame dragging becomes irresistible, where spacetime itself is being dragged faster than any object could move to compensate, is called the ergosphere. It surrounds the event horizon like a flattened shell, somewhat larger at the equator, pinching down to touch the horizon at the poles. Within the ergosphere, all objects and all light are inevitably dragged in the direction of the black hole's spin. There is no hovering. There is no stillness. Spacetime itself is in motion, and everything within it is carried along. A process called the Penrose process allows energy to theoretically be extracted from a rotating black hole's ergosphere, objects interacting just outside the horizon in precisely the right way can escape with more energy than they arrived with, drawing from the rotational energy of the black hole itself. Slowly, across unimaginable timescales, a rotating black hole losing energy this way would spin down. The most rapidly spinning black holes observed are rotating at a significant fraction of the theoretical maximum. Spacetime around them is in violent, continuous rotation. If you could somehow hover near such an object, which ergosphere physics would prevent, you would find that the fabric of spacetime you exist within is moving, not because you are moving through it, but because it is moving, carrying you as a river carries a leaf, with no sensation of flow, no local wind, no local force. Just the quiet, implacable geometry of a universe that does what it does, without asking. Black holes are, in a sense, gravity's final statement. The end point of what happens when mass accumulates without limit, when resistance fails, when the curvature of spacetime is driven to its ultimate conclusion. They are places where time slows to a stop for outside observers, where light cannot escape, where spacetime spirals inward and takes everything with it. And they are common. Astronomers now believe there is a supermassive black hole at the center of nearly every large galaxy, including our own. Sagittarius A star, the black hole at the heart of the Milky Way, contains roughly 4 million times the mass of the Sun, sitting quietly 26,000 light-years away, bending the orbits of nearby stars into tight, rapid ellipses that trace its presence as clearly as anything we can see. In 2019, the Event Horizon Telescope, a network of radio telescopes spanning the entire planet, functioning as a single Earth-sized instrument, produced the first direct image of a black hole's shadow, a dark central region surrounded by a bright ring of superheated gas, the light having bent and circled around the horizon before escaping toward us. It was an image of curved spacetime made visible. A portrait of geometry. We looked at a black hole. And it looked, if not back, then at least real. We left off at the ergosphere, that region surrounding a rotating black hole where spacetime itself is in motion, where nothing can remain still relative to the distant universe. but the ergosphere is only the beginning of what extreme gravity does to the space around these objects. Further out, at distances that can extend to millions of kilometers around the most massive black holes, gravity operates with a different kind of violence. Not the steady, organizing pull that builds galaxies and holds moons in orbit, but a tearing force, tidal disruption, taken to its most dramatic extreme. A star wandering too close to a supermassive black hole does not simply fall in. The side of the star nearest the black hole is pulled significantly more strongly than the far side. The differential, the tidal force, stretches the star along the radial direction and compresses it from the sides, in a process physicists have nicknamed, with characteristic scientific bluntness, spaghettification. If the tidal force exceeds the star's own self-gravity, the force holding it together as a coherent object, the star is torn apart. Shredded. Its material is drawn into a long, winding stream that curves around the black hole, eventually settling into a bright, swirling accretion disk. These tidal disruption events produce flares of radiation visible across billions of light years, bright enough to briefly outshine entire galaxies. We have observed dozens of them. Each one is the death of a star, a sun like ours, perhaps with its own planets, its own history, compressed into a flash of X-rays and ultraviolet light by the geometry of spacetime near a mass millions of times greater than itself. Gravity, at these scales, does not organize. It consumes. But black holes are not the only compact objects where extreme gravity makes its presence felt. Neutron stars, the dense remnants left behind when a massive star collapses and the core survives, held up just barely by the pressure between neutrons pressed to their limits, are laboratories of physics that cannot be reproduced anywhere else. A neutron star typically contains between 1 and 2 solar masses of material compressed into a sphere roughly 20 kilometers across. The density is so extreme that a single teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. Gravity on the surface of a neutron star is approximately 200 billion times stronger than on Earth's surface. At this intensity, gravitational redshift becomes not a subtle correction but a significant observational effect. Light emitted from the surface of a neutron star loses a measurable fraction of its energy climbing out of the gravitational well. The frequency drops, the wavelength stretches, and by the time that light reaches our telescopes, it has shifted noticeably from what was emitted. By carefully measuring this redshift, comparing the observed spectrum to what the emitting atoms are known to produce in a laboratory, astronomers can infer the ratio of a neutron star's mass to its radius, probing the extreme physics of its interior. Inside the neutron star, gravity and neutron degeneracy pressure face each other in a balance of extraordinary tension. Neutron degeneracy pressure is a quantum mechanical effect, a consequence of the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state. As neutrons are squeezed together, they resist further compression not through heat or conventional pressure, but through a fundamental quantum insistence on occupying distinct states. This resistance is what holds the neutron star up. But there is a limit. Above roughly 2 to 3 solar masses, the exact value depends on poorly understood physics deep inside neutron stars. Even neutron degeneracy pressure cannot hold. Gravity wins, and the object collapses further into a black hole. Between the maximum mass of a neutron star and the minimum mass of a stellar origin black hole, there exists a range, roughly 2 to 5 solar masses, where observations have, until recently, found very few objects. This is called the mass gap, and its boundaries and origin remain an active area of research. Gravitational wave detections have begun to populate this range with candidate objects, blurring what once seemed like a sharp boundary and raising new questions about what exactly forms in the most extreme stellar collapses. Now, black holes have long been treated as the ultimate endpoint, objects defined by their singularity and their horizon, characterized entirely by mass, spin, and electric charge. Simple, in a mathematical sense. Almost featureless. But in the 1970s, a series of theoretical insights changed the picture in ways that physicists are still grappling with today. Jacob Bekenstein noticed something peculiar. The laws governing black holes, how their horizons behave, how they respond to matter falling in, how they interact with each other, bore a striking, formal resemblance to the laws of thermodynamics. The area of a black hole's event horizon, he proposed, was analogous to entropy, a measure of disorder, of the number of possible internal configurations consistent with the observable external properties of a system. And crucially, like thermodynamic entropy, the total area of black hole horizons in a closed system could never decrease. This was a mathematical parallel, and it might have remained merely a curiosity. But then Stephen Hawking applied quantum field theory to the region just outside a black hole's event horizon, and found something nobody had expected. Black holes should radiate. In quantum mechanics, empty space is not truly empty. It is filled with fluctuating quantum fields, constantly producing and annihilating pairs of virtual particles in timescales too brief for the pairs to be individually detectable. Near the event horizon, Hawking argued, something different can happen. One particle of a pair falls inside the horizon, while the other escapes. The escaping particle carries away real energy, energy that must ultimately come from the black hole itself. The black hole loses mass. It radiates, very slowly, with a thermal spectrum corresponding to a specific temperature inversely proportional to its mass. This Hawking radiation, as it came to be called, has never been directly observed. For black holes of stellar mass or above, the temperature is so extraordinarily low, far colder than the cosmic microwave background radiation that fills the universe, that the signal is completely undetectable with any current or foreseeable instrument. But the theoretical derivation is considered robust, and its implications are profound. If black holes have temperature, they have thermodynamic properties. If they have entropy, they have internal degrees of freedom, some number of underlying quantum states encoded in the horizon. The Bekenstein-Hawking entropy formula assigns to a black hole an entropy proportional to the area of its event horizon, measured in units of the Planck length squared. This number is staggeringly large. For a stellar mass black hole, it is on the order of 10 to the power of 77. Each unit represents, in some sense, one bit of information about the interior. This is the point where gravity reaches toward quantum mechanics and the two frameworks, which have refused to be unified for a century, begin to press against each other in the most uncomfortable way. If a black hole radiates and slowly evaporates, what happens to the information encoded in everything that ever fell into it? Quantum mechanics insists that information is conserved, that the complete quantum state of a system can always, in principle, be recovered from its future evolution. But if a black hole evaporates entirely, and if Hawking radiation carries no information about what fell in, then that information appears to be destroyed. Gone. Not transformed, not hidden, simply absent from the universe. This is the black hole information paradox, and it has occupied some of the most brilliant minds in theoretical physics for 50 years. It is not a paradox in the popular sense of a pleasing puzzle. It is a genuine conflict between two foundational frameworks of physics, general relativity and quantum mechanics, that cannot both be fully correct as currently formulated. One of them must yield, or both must be replaced by something deeper. Various resolutions have been proposed. Hawking radiation might, after all, carry subtle correlations encoding information about the interior, just in a form too complex to extract practically. The information might escape in the final explosive moments of evaporation. Spacetime might develop features called firewalls at the horizon, resolving the paradox at the cost of burning anything that crosses. The interior might not exist in the way classical general relativity suggests. None of these proposals has achieved consensus. The information paradox points to something that physicists widely believe: general relativity is not the final word. Somewhere, at the intersection of gravity and quantum theory, there is a deeper framework waiting to be found. Black holes are the place where the absence of that framework is most acutely felt. And then there is one more thread, quieter than the others, but worth following. In the very early universe, in the first fractions of a second after the Big Bang, conditions were so extreme, densities so high, fluctuations in the energy density so large, that regions of space may have been compressed directly into black holes without any star needing to form first. These are called primordial black holes, and they are among the most speculative but persistently interesting objects in theoretical cosmology. Depending on when they formed and how large the density fluctuations were, primordial black holes could span an enormous range of masses, from objects lighter than an asteroid, which would have evaporated via Hawking radiation long ago, to objects massive enough to have survived to the present day and potentially contribute to the dark matter content of the universe. The idea that dark matter might be, at least partly, composed of primordial black holes has waxed and waned in favor over decades. Many mass ranges have been observationally constrained or ruled out. If too many primordial black holes of a given mass existed, they would leave detectable signatures in gravitational lensing surveys, in the cosmic microwave background, in the disruption of dwarf galaxies. But certain mass windows remain open, and the question has not been definitively closed. Gravitational wave observatories have added a new dimension to the search. Some of the black hole mergers detected by LIGO and Virgo have involved masses or mass ratios that are difficult to explain through conventional stellar evolution, and primordial black holes have been proposed as candidates, though stellar physics can likely account for most observations without invoking them. What is striking is that the same force, gravity, that holds your feet to the ground and keeps the moon in its orbit also, in the extreme conditions of the early universe, may have spontaneously created black holes from the fabric of spacetime itself, before any star had ignited, before any galaxy had formed, seeding the cosmos with compact objects whose influence on the universe's subsequent history we are still trying to understand. Gravity is present at the beginning. It is present at the end. It operates at every scale, from the human to the cosmic, from the slow drift of tides to the violent shredding of stars, from the quantum fluctuations at a black hole's horizon to the large-scale structure of the observable universe. And still, at its deepest level, where quantum mechanics and spacetime meet, it remains, quietly, a mystery. There is a kind of event that happens in the universe, has been happening since long before our solar system existed, that sends a shudder through the fabric of spacetime itself. Not a metaphorical shudder. A physical one. A propagating distortion in the geometry of space and time, moving outward at the speed of light, carrying the imprint of whatever violent motion produced it. We call them gravitational waves. And for most of human history, we had no idea they were passing through us. The origin of gravitational waves lies in a prediction that follows naturally from general relativity. When mass accelerates, not just moves, but accelerates, changes its velocity, curves its path, it disturbs the curvature of the surrounding spacetime. That disturbance does not stay local. It propagates outward as a wave, alternately stretching space in one direction and compressing it in the perpendicular direction, then reversing, oscillating as it travels. The effect is transverse, like a ripple on the surface of a pond, but the medium being rippled is spacetime itself. A single oscillating mass produces some gravitational radiation, but the geometry of the situation limits what a spherically symmetric system can emit. The most efficient sources are asymmetric, two massive objects orbiting each other, or a rapidly rotating deformed object, or any large mass moving in a way that breaks the symmetry of the gravitational field. Binary systems, in particular, are natural gravitational wave factories. These waves travel at the speed of light, as confirmed by a single extraordinary observation in 2017 that we will return to shortly. They carry energy away from the system that produces them. They interact extraordinarily weakly with matter, passing through the Earth, through stars, through everything, essentially unimpeded. This is what makes them so difficult to detect, and also what makes them so valuable as astronomical tools. A gravitational wave carries information about its source with almost no distortion, no absorption, no scattering. It arrives essentially unchanged from the moment of its creation. The idea that gravitational waves could be detected directly was, for most of the 20th century, considered somewhere between extremely difficult and practically impossible. The waves produced even by catastrophic cosmic events stretch and compress space by amounts that are, at Earth, almost incomprehensibly small. A typical gravitational wave from a stellar mass binary merger would change the distance between 2 points separated by 4 kilometers by roughly 1/10,000th the diameter of a proton. To measure this, you would need an instrument of almost unimaginable precision. You would need to isolate it from every vibration, from traffic, from ocean waves, from seismic noise, from thermal fluctuations in the mirrors and the light itself. You would need lasers stable enough to measure path length differences smaller than any physical structure is wide. You would need to do all of this at two separate locations, widely separated, so that local noise could be distinguished from a real spacetime signal arriving at both sites. This is what LIGO is. The Laser Interferometer Gravitational Wave Observatory, with facilities in Louisiana and Washington State, each consisting of two 4-kilometer vacuum tubes arranged in an L shape, bouncing laser light back and forth between suspended mirrors, looking for the almost impossibly subtle signature of a passing gravitational wave. On September 14, 2015, at 5:51 in the morning Eastern Time, both detectors registered a signal. It lasted less than a second. It swept upward in frequency from roughly 35 Hz to 150 Hz, a chirp, physicists called it, and then it was gone. The signal arrived at the Louisiana detector 7 milliseconds before Washington, consistent with a wave traveling at the speed of light from a direction in the southern sky. The analysis that followed confirmed what the signal was: two black holes, each roughly 30 solar masses, in their final moments of inspiral, merging into a single black hole of approximately 62 solar masses. 3 solar masses of energy had been released as gravitational waves in a fraction of a second, more power, briefly, than all the stars in the observable universe combined, released entirely as ripples in space-time. And it had happened more than 1 billion light-years away. When the detection was announced in February 2016, it was not merely news of a discovery. It was the opening of a new sense. For all of human history, we had understood the universe through light, through electromagnetic radiation of every frequency, from radio waves to gamma rays. Gravitational waves are something else entirely. They are not light. They do not interact with matter the way light does. They carry information about events that produce no light at all, colliding black holes, for instance, which are by definition dark. LIGO had given astronomy a new way of listening to the universe, and on its very first detection, it had heard something spectacular. To understand why LIGO was hearing anything at all, it helps to understand what happens to binary systems over time. Two massive objects orbiting each other, two neutron stars, two black holes, or one of each, are not in a stable, permanent configuration. As they orbit, they emit gravitational waves, and those waves carry energy away from the system. With each orbit, the system has slightly less total energy. The objects draw imperceptibly closer. The orbit shrinks. As the orbit shrinks, the objects must move faster to remain in orbit, and moving faster means more energy radiated per unit time, which means they draw closer still, faster still. The process is self-accelerating, a slow spiral that can persist for billions of years at large separations, then rapidly steepen as the objects approach each other, culminating in a final plunge and merger in a fraction of a second. This is what the LIGO chirp captures. The rising frequency and amplitude of the signal trace the final moments of the inspiral, the objects speeding up, circling faster, the gravitational waves coming more rapidly and carrying more energy, until the two objects become one. The chirp is, in a very literal sense, the sound of a binary system spending the last of its orbital energy. The first indirect evidence for gravitational wave emission came decades before LIGO. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars in orbit around each other, one of them a pulsar whose radio pulses allowed its orbit to be tracked with extraordinary precision. Over years of observation, the orbital period was found to be decreasing at exactly the rate predicted by general relativity for a system losing energy to gravitational radiation. The agreement between observation and theory was, and remains, essentially perfect. Hulse and Taylor received the Nobel Prize in 1993 for this indirect detection, the first confirmation that gravitational waves were real and behaving exactly as Einstein's equations predicted. But the waves themselves carry consequences that go beyond simply draining energy from a system. As gravitational waves propagate outward from their source, they exert what is called a gravitational back reaction on the system producing them. The emission of radiation is not passive. It actively alters the motion of the source. In a binary spiral, the back reaction is what drives the orbital decay. The radiation carries away angular momentum and energy, and the orbit responds by tightening. The source shapes the wave, and the wave reshapes the source, in a continuous dynamic exchange. In the final moments of a black hole merger, when the two objects are moving at a significant fraction of the speed of light and the gravitational wave emission is most intense, the back reaction becomes a dominant force in the dynamics. The system is no longer well described by any simple approximation. It is a fully nonlinear, highly dynamic spacetime, and modeling it correctly requires numerical relativity, solving Einstein's field equations directly on supercomputers, letting the geometry of spacetime itself evolve in time. The gravitational wave signal from a merger carries a memory. Not memory in any metaphorical sense, but a physical one. After the wave passes and the oscillations settle, space-time does not quite return to its original configuration. There is a permanent, residual displacement, a shift in the relative positions of freely floating objects that does not oscillate away. This is called the gravitational wave memory effect, or the Christodoulou memory, and it is particularly pronounced for asymmetric mergers, where the gravitational wave emission is stronger in some directions than others. The memory encodes something about the total radiated energy and its directionality, a lasting imprint left on the geometry of space. And asymmetric emission has another dramatic consequence. When two black holes merge and the gravitational wave emission is not perfectly symmetric, which it generally is not, unless the masses and spins are arranged in a very particular way, the merged object receives a recoil. A kick. By Newton's third law translated into relativistic terms, the momentum carried away asymmetrically by gravitational waves must be compensated by momentum imparted to the remnant. For typical mergers, this kick velocity is hundreds of kilometers per second. For the most extreme configurations, where the component spins are large and oriented in particular directions, the kick can reach several thousand kilometers per second. This is fast enough to eject the merged black hole entirely from its host galaxy. A black hole formed in the dense stellar environment at the center of a galaxy, if it receives the right kick at merger, can be launched on a trajectory that carries it out of the galaxy entirely, into the intergalactic void, where it wanders indefinitely. Astronomers have found candidate examples, supermassive black holes displaced from the centers of their host galaxies, or moving with anomalously high velocities, that may be the aftermath of such recoil events. Gravity, in its most violent expression, can exile the very objects it creates. Neutron stars, too, participate in this gravitational wave physics, though in a quieter way. A perfectly spherical spinning neutron star radiates no gravitational waves. Spherical symmetry means no oscillating mass quadrupole, and therefore no wave emission. But neutron stars are not perfectly spherical. Some have small deformations, mountains, in the loose sense, bumps in the crust no more than a centimeter or two high but distributed asymmetrically around the rotation axis. As the neutron star spins, this asymmetry sweeps around, generating a continuous, low-amplitude gravitational wave signal at twice the rotation frequency. Over time, this emission carries away rotational energy. The neutron star spins down. The effect is small, and for most pulsars, electromagnetic radiation and particle winds carry away far more energy than gravitational waves. But for some rapidly rotating neutron stars, millisecond pulsars, spinning hundreds of times per second, gravitational wave emission may contribute meaningfully to their long-term spin evolution. Advanced detectors are searching for these continuous wave signals, which would confirm both the existence of neutron star deformations and provide a new way to probe their interior structure. The 2017 detection that confirmed gravitational waves travel at the speed of light deserves its own moment. Two LIGO detectors and the Virgo detector in Italy recorded a gravitational wave signal from the merger of two neutron stars. Less than 2 seconds later, the Fermi and Integral space telescopes detected a short gamma-ray burst from the same direction. The gravitational waves and the light arrived at Earth separated by 1.7 seconds, after traveling for approximately 130 million light-years. This placed the difference in their speeds at less than 1 part in 10 to the 15th, confirming that gravitational waves travel at the speed of light to extraordinary precision. That observation also produced a fireball visible in optical and infrared telescopes for weeks, a kilonova, the glowing debris of two neutron stars merging, rich in heavy elements forged in the collision. Gold, platinum, uranium. Elements heavier than iron that cannot be produced in ordinary stellar fusion, created in quantity only in the extreme conditions of a neutron star merger and scattered into the universe by the explosion. The gold in a ring on your finger, or anywhere else on Earth, was very likely forged in an event like that one, two neutron stars spiraling together over billions of years, their orbit decaying through gravitational wave emission, until in a final fraction of a second they collided and scattered their contents across a region of space that, eventually, became part of the cloud that formed our solar system. Gravity, in a sense, made that gold possible. The long and spiral, the wave emission, the merger, all of it driven by the same geometric curvature of spacetime that holds you to the ground right now. Everything is connected. The waves, the gold, the ground beneath you. All of it, gravity. Pull back, now. Pull back from the detectors and the mergers and the rippling geometry of spacetime near compact objects. Pull back until until the solar system is a small warm region in one arm of an ordinary spiral galaxy, until the galaxy itself is one of hundreds of billions scattered across a universe so large that light takes tens of billions of years to cross it. At this scale, one force dominates everything. Not electromagnetism, which is stronger but cancels itself out across large distances as positive and negative charges balance. Not the nuclear forces, which operate only at subatomic ranges. At the scale of galaxies and the large-scale structure of the universe, gravity stands alone, the only force with effectively infinite range, the only force with no opposing charge, the only force that never cancels. Gravity is the architect of the cosmos. And the story of how it built everything we can see begins not with stars or galaxies, but with something almost imperceptibly small. In the very early universe, shortly after the Big Bang, matter was distributed through space with extraordinary smoothness. But not perfect smoothness. There were fluctuations, regions that were fractionally, almost undetectably denser than their surroundings. The density contrast was roughly 1 part in 100,000. If the universe had been a perfectly flat ocean, these fluctuations would have been ripples less than a millimeter high across a surface spanning a continent. These tiny overdensities were the seeds of everything. Gravity is patient, and it is relentless. A region that is even slightly denser than its surroundings exerts a slightly stronger gravitational pull on the matter around it. That matter drifts inward, very slowly at first. As it arrives, the region grows denser still. A denser region pulls more strongly. More matter arrives. The process compounds over time, and across hundreds of millions of years, what began as an almost imperceptible wrinkle in the density of the early universe grows into something vast and structured, a filament, a wall, a cluster of galaxies. But where did those initial fluctuations come from? The leading answer reaches back to an era even earlier than the smooth, hot plasma of the early universe, to a period called inflation, thought to have occurred in the first tiny fraction of the first second after the Big Bang. During inflation, the universe expanded exponentially, doubling in size again and again in an extraordinarily short time. At the quantum level, fields cannot be perfectly uniform, quantum mechanics forbids it. Tiny quantum fluctuations in the inflaton field, the hypothetical field driving inflation, were stretched by this exponential expansion to macroscopic scales, imprinted across the universe as density variations that would persist and grow for billions of years. In this picture, the largest structures in the observable universe, superclusters, the great walls and filaments of the cosmic web, trace their origin to quantum fluctuations smaller than any scale we can directly probe. Gravity took those whispers and amplified them, over billions of years, into the architecture of the cosmos. The evidence for this is written in the cosmic microwave background, the faint glow of light left over from when the universe was roughly 380,000 years old, when it had cooled enough for electrons and protons to combine into neutral hydrogen, and the universe became transparent for the first time. That ancient light has been traveling ever since, and it carries a map. Tiny temperature variations in the cosmic microwave background, again, roughly 1 part in 100,000, correspond directly to the density fluctuations of the early universe. Where the light is fractionally warmer, matter was slightly denser. Where it is fractionally cooler, matter was slightly more sparse. The pattern of these fluctuations, their statistical distribution across different angular scales, encodes an enormous amount of information about the early universe, its age, its composition, its geometry, the spectrum of primordial fluctuations seeded by inflation. And gravity's imprint is there, clearly readable. Sound waves propagating through the hot plasma of the early universe, driven by the interplay of gravitational attraction and radiation pressure, left a characteristic scale imprinted in both the cosmic microwave background and the distribution of galaxies we observe today. This scale, the baryon acoustic oscillation scale, appears as a subtle preferred separation distance between galaxy clusters, a relic of the universe's acoustic physics in its first few 100,000 years. We can measure it. We can use it as a standard ruler to probe the geometry and expansion history of the universe. It is one of the most powerful tools in modern cosmology. All of it gravity's doing, written in the oldest light in the universe. As structure grew and matter clustered, the overdense regions eventually reached a threshold, a point at which the gravitational pull inward overcame the thermal pressure pushing outward, and collapse became inevitable. This threshold is described by what physicists call the Jeans instability, after the British physicist James Jeans, who analyzed it in the early 20th century. The Jeans criterion is essentially a competition between gravity and pressure. A cloud of gas will remain stable, will not collapse, if it is below a critical mass and size, where pressure gradients can respond quickly enough to resist gravitational infall. But if the cloud is massive enough, or cold enough, or dense enough, gravity wins. The cloud begins to contract. As it does, it heats up, gravitational potential energy converting to thermal energy, but if the gas can radiate that heat away quickly enough, the collapse continues. The cloud fragments, collapses further, and eventually the first knots of dense gas ignite as stars. This is how every star in the universe was born. Gravity, acting on a region of gas that crossed the Jeans threshold, pulled it together against all resistance, compressed it until nuclear fusion ignited, and in doing so created a new sun. The process is not simple or clean. A collapsing gas cloud does not fall straight inward as a single object. Gravity, acting on different regions within the cloud, creates a turbulent, fragmented collapse. Denser pockets within the cloud collapse faster than surrounding regions. Subclouds form within clouds, each following its own gravitational trajectory. The result is not a single star but typically a cluster, dozens or hundreds of stars forming roughly simultaneously from the same parent cloud, then dispersing over millions of years as the gravitational binding of the cluster gradually dissolves. Magnetic fields thread through interstellar gas clouds, providing additional resistance to collapse and channeling the geometry of the infalling material. Angular momentum, the tendency of any rotating system to spin faster as it contracts, like a figure skater pulling in their arms, causes collapsing clouds to flatten into disks. Gravity is the driver, but the material it works with carries its own properties that shape the outcome. And even before collapse reaches the point of star formation, gravity focuses interstellar gas into dense regions through a more gradual process. Along the spiral arms of galaxies, density waves compress the interstellar medium as it passes through, triggering star formation in organized patterns. The long, glowing chains of young blue stars that trace spiral arms are not random. They follow the compression zones where gravity has concentrated gas above the Jeans threshold. The beautiful structure of a spiral galaxy is, in large part, a map of where gravity has been concentrating gas over billions of years. Inside a star, once it forms, gravity continues to shape the dynamics in ways that are easy to overlook from the outside. The interior of a star is not a static, uniform ball of hot gas. It is a continuously churning, circulating system, driven by the interplay of gravity and heat. In regions where energy transport by radiation alone is insufficient, where the temperature gradient is too steep, the gas becomes convectively unstable. Hotter, less dense parcels of gas rise buoyantly upward, cooler, denser parcels sink under gravity, and the result is convective circulation, large-scale overturning motions that carry heat from the deep interior toward the surface far more efficiently than radiation alone could manage. The Sun has a deep radiative zone, where energy moves slowly outward as photons are absorbed and re-emitted billions of times, and an outer convective zone roughly 200,000 kilometers thick, where churning convective cells carry energy to the surface. The granulation visible on the Sun's surface, the constantly shifting pattern of bright cells and darker boundaries, is the top of this convective layer, where hot material arrives from below, releases its energy as light, cools, and sinks again. More massive stars are convective in their cores and radiative in their outer layers. Less massive stars, like our Sun, reverse this pattern. The details depend on how steeply temperature varies with depth, and how efficiently the gas can radiate heat, but in every case, it is gravity that sets up the temperature gradient that drives the circulation in the first place. The same process operates inside planets. Earth's outer core, a vast ocean of liquid iron thousands of kilometers below the surface, is in a state of continuous convective motion, hotter material rising, cooler material sinking, the whole system driven by the heat left over from Earth's formation and from the ongoing radioactive decay of elements in the interior. This convection is what generates Earth's magnetic field, as the moving conducting liquid acts as a dynamo. Without gravity maintaining the temperature gradient that drives the convection, the magnetic field would eventually die, and without the magnetic field, Earth's surface would be far more directly exposed to the solar wind. Gravity built the field that shields us. The chain of causation, traced back, always leads there. And at the center of every star, gravity's most fundamental role in stellar physics is the constant pressure it exerts inward, the weight of the entire star pressing down on its own core. This is what nuclear fusion must resist. The balance between gravitational compression and the outward pressure from fusion, thermal pressure, radiation pressure, the energy released by nuclear reactions, is what defines a star's size, temperature, luminosity, and lifespan. A more massive star has stronger gravitational compression. To resist it, the core must run its fusion reactions faster, at higher temperatures, burning through its fuel more quickly. The most massive stars, 100 times the mass of the Sun, are enormously luminous but live only a few million years before their fuel is exhausted. The Sun, a modest middle-aged star, has been burning for about 4.6 billion years and has roughly as long again to go. The smallest, dimmest red dwarf stars, where gravity's compression is gentler, burn so slowly and so efficiently that they may remain on the main sequence for trillions of years, far longer than the current age of the universe. A star's lifespan is, in a very direct sense, a negotiation between gravity and nuclear physics, how strongly the star's mass presses inward, and how quickly the available fuel can be converted into the pressure that holds it out. When the fuel runs low and the fusion rate drops, gravity gets the final word. The star contracts, often dramatically, its fate determined by how much mass remains. A white dwarf, a neutron star, a black hole, each one a different answer to the question of how much mass the remaining pressure can hold against the inward pull. Every star in the sky is that negotiation, in progress, right now. And it all began with gravity noticing, billions of years ago, that one small region of gas was very slightly denser than the space around it, and pulling it, patiently, inward. There is a principle at work inside every star, a kind of gravitational accounting that determines whether a self-gravitating system is stable, contracting, or expanding. Physicists call it the virial theorem, and it connects the average kinetic energy of a system to its average gravitational potential energy in a precise and elegant way. For a gravitationally bound system in equilibrium, a star, a galaxy, a cluster of galaxies, the average kinetic energy is equal to exactly half the magnitude of the average potential energy, with opposite sign. What this means in practice is that a system which loses energy does not simply cool down and sit still. It contracts. As it contracts, its gravitational potential energy decreases, and by the virial theorem, its kinetic energy, the thermal motion of its particles, actually increases. The system gets hotter as it loses energy. This is one of the most counterintuitive behaviors in astrophysics, and it has profound consequences. A star that loses energy from its surface does not cool uniformly. Its core contracts and heats up, driving faster nuclear reactions, which produce more energy, which the star radiates away from its surface, which causes more contraction, in a self-regulating cycle that can persist for billions of years. The virial theorem is what makes stars thermostats, self-correcting systems that maintain their balance against both collapse and expansion across timescales that dwarf the history of life on Earth. The same principle governs much larger systems. A galaxy is, in a broad sense, a virially balanced system, the kinetic energy of its star's orbital motions balanced against the gravitational potential of all the mass they move within. When astronomers measure the velocities of stars in galaxies, or the velocities of galaxies in clusters, and find that they are moving far too fast to be accounted for by the visible mass alone, it is the virial theorem that makes this discrepancy so telling. The motions reveal the total gravitational potential. And the total gravitational potential reveals far more mass than we can see. Dark matter, again, inferred from the dynamics of gravity, before any direct detection. Galaxies themselves are gravity's most visible large-scale creations. The process of galaxy formation began when the first density fluctuations we discussed had grown large enough, through gravitational amplification, to collapse into the first halos of dark matter, vast, roughly spherical clouds of invisible mass that formed the gravitational scaffolding within which ordinary gas could collect, cool, and condense into stars. The first galaxies were small by today's standards, turbulent and irregular, forming in a universe that was only a few 100 million years old and still assembling itself. Over cosmic time, gravity continued its work. Small galaxies merged with other small galaxies. Gas continued to fall in long filaments. Dark matter halos grew by accreting other halos. The hierarchical process of structure formation, smaller structures assembling into larger ones, built the diverse population of galaxies we observe today: ellipticals, spirals, lenticulars, irregulars, each shaped by its particular history of mergers, accretion, and the quiet internal dynamics of gravity acting on billions of orbiting stars. At a larger scale still, gravity pulls galaxies into groups and clusters. Our own Milky Way belongs to a modest gathering called the Local Group, a few dozen galaxies, dominated by the Milky Way and the Andromeda Galaxy, spread across a region roughly 10 million light-years across. The Local Group is gravitationally bound. Its members will not drift apart with the expansion of the universe. Andromeda and the Milky Way are, in fact, approaching each other, drawn together by their mutual gravity, and will merge in roughly 4 to 5 billion years in a slow, graceful collision that will reshape both galaxies over hundreds of millions of years into a single large elliptical. Richer environments exist. Galaxy clusters, the most massive gravitationally bound objects in the universe, contain hundreds to thousands of galaxies, along with enormous quantities of hot gas and dark matter, all bound within a common gravitational potential well spanning tens of millions of light-years. The total mass of a large cluster can reach 1,000 trillion times the mass of the Sun. Not all clusters are the same, and gravity is the reason. Some clusters are dynamically relaxed. Their galaxies have been orbiting within the common potential for billions of years. The hot gas has settled into a smooth, roughly spherical distribution, and the system has reached a kind of gravitational equilibrium. These relaxed clusters have a characteristic appearance, a roughly symmetric halo of X-ray emitting gas, a single dominant galaxy at the center, and a population of smaller galaxies distributed in a smooth, regular pattern around it. Others are still evolving, caught in the process of merging with another cluster, their gas sloshing and shocking, their galaxy populations interleaved and disrupted, the gravitational potential still shifting as the two mass concentrations pass through each other or slowly combine. The Bullet Cluster, two galaxy clusters that have recently passed through each other, is one of the most famous examples, and one of the most compelling pieces of evidence for dark matter, because the hot gas of the two clusters was slowed by electromagnetic interactions during the collision while the dark matter halos passed through each other almost unimpeded, leaving the gravitational mass separated from the visible gas in a way that is essentially impossible to explain without invoking dark matter. Within clusters, gravity sorts galaxies by mass in a process called dynamical friction. More massive galaxies moving through the cluster interact gravitationally with the surrounding distribution of smaller galaxies and dark matter, losing energy through these interactions and sinking toward the center of the potential well over time. This is why the most massive, Often most recently merged giant elliptical galaxies tend to sit at the centers of rich clusters. Gravity has pulled them there, through countless small interactions, over billions of years. Step back further still, and the full architecture of the universe becomes visible. The cosmic web, the large-scale structure of the observable universe, is the most extensive gravitational construction in existence. It consists of vast filaments of matter, hundreds of millions of light-years long, intersecting at dense nodes where galaxy clusters accumulate. Between the filaments lie enormous voids, regions of space, hundreds of millions of light-years across, that contain almost no galaxies, almost no matter of any kind. This structure did not appear suddenly. It grew, continuously, from the tiny primordial fluctuations we discussed, through gravitational amplification operating across billions of years. The pattern it produced, its statistical properties, the characteristic sizes of filaments and voids, the distribution of cluster masses, is one of the primary observational tools of modern cosmology, encoding information about the universe's composition, the nature of dark matter, and the properties of dark energy. Matter flows along the cosmic filaments. Gas and dark matter, responding to the gravitational landscape, stream along the filaments toward the dense nodes at their intersections, feeding galaxy clusters with a continuous supply of new material. This cosmic accretion is not uniform or steady, it is lumpy, directional, organized by the geometry of the web itself. Galaxies caught in the flow of a filament tend to align their rotation axes with the filament direction, a subtle statistical signature of the gravitational environment they formed in. And the voids are not merely empty. They are actively emptying. As matter flows gravitationally toward the overdense filaments and clusters, the underdense regions are progressively drained. Galaxies in or near voids feel a net gravitational pull away from the void center, toward the surrounding structures, and over time they migrate outward along the void walls and into the filaments. The void grows emptier, its boundaries sharpen, and it expands, not because the universe is creating new empty space, but because gravity is systematically evacuating what was already there. Voids are, in a sense, the universe breathing out the spaces left behind as gravity draws matter toward structure. On scales above a few 100 million light-years, the universe begins to look smooth. The cosmic web, for all its detail at smaller scales, gives way to a rough homogeneity when averaged over sufficiently large volumes. This is the cosmological principle, the assumption, well supported by observation, that the universe looks broadly the same in all directions and from all locations at the largest scales. Gravity, the great organizer, has built structure everywhere but in ways that are statistically uniform across the whole. And now the cosmic web is slowing down. In the universe's early history, matter was denser, gravity was stronger across shorter distances, and the growth of structure was vigorous. Density fluctuations amplified quickly. Filaments formed, clusters assembled, the web built itself with cosmic urgency. But the universe is also expanding, and that expansion is accelerating, driven by dark energy, a mysterious component of the universe whose effect is to push space apart at an ever-increasing rate. As dark energy takes hold and the expansion accelerates, gravitational growth becomes harder. Overdense regions can still accrete matter from their immediate surroundings, but pulling in material from increasingly large distances becomes progressively less effective as the expansion carries that material away faster than gravity can draw it in. New large-scale structures stop forming. The cosmic web, at its grandest scales, effectively freezes, the pattern it has reached, becoming the permanent architecture of the universe going forward. What exists now in the cosmic web is, more or less, what will always exist. The clusters will continue to grow slowly by absorbing their immediate surroundings, and eventually the local group will merge into a single large galaxy as Andromeda and the Milky Way combine. But the great work of large-scale structure formation is, in a cosmological sense, winding down. The universe has done most of its gravitational building. What remains will drift apart, slowly, as the expansion carries isolated structures away from each other across distances that light will eventually no longer be able to cross. In the far future, tens of billions of years from now, the observable universe from any given galaxy will shrink as other galaxies recede beyond the horizon. The cosmic web that we can map today, with its filaments stretching across billions of light years, will be invisible to observers of the distant future, who will see only their own local gravitational island, surrounded by an expanding darkness. But that is the universe making its slow choices. For now, the web is here. The filaments are here. The clusters are here, still assembling, still virializing, still being shaped by the same patient force that gathered the first wisps of gas in the first moments of cosmic history. Gravity built all of this. One small pull at a time, across billions of years, until the universe looked like what it is. For most of this journey, we have watched gravity build things. Pull things together. Organize, collapse, cluster, bind. Gravity is the great assembler, drawing matter from the void into stars and galaxies and the vast architecture of the cosmic web. But the universe has another tendency. A counter-tendency. Something that works in the opposite direction, pushing outward on the largest scales, driving space itself apart. And gravity's relationship with this opposing force is one of the deepest and most unresolved questions in all of science. We call it dark energy. And to understand what it does, it helps to first understand what it is not. Dark energy is not matter. It does not cluster. It does not respond to gravity the way ordinary mass or even dark matter does. It appears to be a property of space itself, a kind of energy inherent in the vacuum, present everywhere uniformly, not diluting as the universe expands, not concentrating in galaxies or filaments. In the language of general relativity, it enters the equations as a term with a very particular character. It behaves like a fluid with negative pressure. This is the critical point, and it is worth sitting with. In general relativity, as we established, it is not just mass but the full stress-energy content of a region that curves spacetime, including pressure. Ordinary matter and radiation have positive pressure, and their gravity is attractive. But dark energy has negative pressure, of a specific magnitude relative to its energy density, and the gravitational effect of this combination is repulsive. Not locally, you cannot feel dark energy pushing you away from the ground. But on the largest scales, where it accumulates across billions of light-years of space, the repulsive effect of dark energy overwhelms the attractive gravity of all the matter in the universe and drives the expansion of space to accelerate. This acceleration was discovered in 1998, when two independent teams of astronomers studying distant supernovae found that the universe was not just expanding, it was expanding faster than it used to be. The universe's expansion is speeding up. Every distant galaxy is receding from us, and the rate of recession is increasing. The finding was so unexpected, so contrary to what gravitational theory alone would predict, that it was greeted with widespread skepticism before the evidence became overwhelming. The teams responsible shared the Nobel Prize in 2011. Dark energy now appears to make up roughly 68% of the total energy content of the universe. Dark matter comprises about 27%. All the ordinary matter, every star, planet, gas cloud, galaxy, and human being, accounts for only about 5% of what exists. Gravity, the force we have been tracing through this entire journey, is the dominant influence on the 5% we can see and the 27% we can infer. Dark energy governs the 68% we barely understand at all. The competition between gravity and dark energy plays out across the entire history of the universe, and it is written into the geometry of space itself. There is a concept in cosmology called the critical density, a specific value of the total energy density of the universe at which space is geometrically flat, on the largest scales. If the actual density of the universe exactly equals the critical density, the universe is flat. Parallel lines remain parallel across cosmic distances. The angles of a triangle sum to exactly 180 degrees. The geometry of space is Euclidean. If the density exceeds the critical density, space curves positively, like the surface of a sphere. If it falls below, space curves negatively, like the surface of a saddle. Observations of the cosmic microwave background, particularly the precise angular scales of its temperature fluctuations, are sensitive to this geometry. And the data tell us that the universe is flat, or very close to it, to within the precision of our best measurements. The total energy density is consistent with the critical value. Gravity, dark energy, dark matter, and ordinary matter have conspired, through mechanisms we do not fully understand, to produce a universe that sits almost exactly at this geometric boundary. Whether this is a profound physical principle, a consequence of inflation, or a remarkable coincidence remains an open question. Across cosmic time, gravity and dark energy have taken turns dominating the universe's behavior. In the first billions of years, the universe was denser, matter was more closely packed, and gravitational attraction dominated the dynamics. The expansion was slowing down. Structure was growing vigorously. Then, roughly 5 billion years ago, as the universe expanded and the density of matter diluted, dark energy, which does not dilute, which maintains the same density as space expands, gradually came to dominate. The expansion stopped decelerating and began to accelerate. The growth of large-scale structure slowed. We live near the transition between these two eras. In cosmological terms, we are at a somewhat special moment, early enough that the large-scale structure built during the matter-dominated era is still observable, late enough that we can measure the acceleration that dark energy is now driving. Future observers, in a universe far more dominated by dark energy, will find much of this evidence erased. There is a thread here that connects gravity not just to space but to time, specifically, to the direction of time. The universe began in an extraordinarily smooth, low-entropy state. Gravity then spent billions of years building structure, pulling matter from near uniformity into the rich, complex hierarchy of stars, galaxies, and clusters. In doing so, it enormously increased the entropy of the universe. This might seem paradoxical. Structure looks ordered. How can building structure increase disorder? The resolution lies in the gravitational degrees of freedom. When matter is smoothly distributed, the gravitational field has low entropy. There are very few ways to arrange it. As gravity clumps matter together, the gravitational degrees of freedom become enormously more varied. The specific arrangement of masses, orbits, velocities, and configurations accessible to the system explodes in number. The entropy of the gravitational field increases dramatically, far outweighing the local decrease in entropy as gas clouds collapse into stars. This is the deep reason for the arrow of time, the direction from past to future, from order to disorder, from smooth beginnings to complex structure. The second law of thermodynamics, which says that total entropy always increases, plays out on a cosmic scale as the gravitational degrees of freedom of the universe grow from their initial simplicity into the elaborate, textured complexity we see around us. Gravity is not just building the universe. It is driving time forward. Back reaction, the influence of small-scale structure on large-scale cosmic dynamics, is a more subtle point, and one that remains actively debated in cosmology. The universe, in our standard models, is treated as smooth and homogeneous on the largest scales, with structure appearing as perturbations on top of a uniform background. But the real universe is not smooth. It is lumpy, full of stars, galaxies, clusters, and voids, and some physicists have argued that this lumpiness, fed back into the equations governing large-scale expansion, might produce corrections to the cosmic dynamics that are not fully captured by the standard models. The magnitude of these back reaction effects is contested. Some researchers argue they are negligible. Others suggest they could be meaningful enough to partly account for what we attribute to dark energy. The question touches on deep issues in how we average general relativity across scales, and it has not been definitively resolved. What it illustrates is that gravity is not simple even when we think we have described it. The nonlinearity we identified earlier, the self-interaction of the gravitational field, continues to create subtleties even at the largest scales. And then there is the vacuum. Quantum field theory predicts that empty space is not truly empty. Virtual particles continuously fluctuate in and out of existence, and these fluctuations carry energy, the zero-point energy of the quantum vacuum. This vacuum energy should, in principle, gravitate. It should contribute to the curvature of spacetime, just as any other form of energy does. And when physicists calculate how much vacuum energy quantum field theory predicts and compare it to the observed value of dark energy, the cosmological constant, the discrepancy is extraordinary. the theoretical prediction is larger than the observed value by somewhere between 60 and 120 orders of magnitude, depending on the energy scale at which the calculation is cut off. This is the cosmological constant problem, and it is widely considered the worst prediction in the history of physics, not because the theory is wrong in its structure, but because something unknown is canceling the vacuum energy to an almost perfect degree, leaving only the tiny residual we observe as dark energy. What mechanism achieves this cancellation, and why it leaves the value it does, remains completely unknown. It is a place where gravity and quantum mechanics press against each other again, producing not a paradox this time but a number so wrong that it suggests our understanding of one or both frameworks is profoundly incomplete. Gravity shapes the voids as it shapes the clusters, and in doing so, it structures the darkness as thoroughly as it structures the light. The voids of the cosmic web are not featureless. They contain a residual population of galaxies, small and relatively isolated, following the gentle gravitational flow that is slowly emptying their surroundings. The largest voids produce a subtle imprint on the cosmic microwave background through a process called the integrated Sachs-Wolf effect, as photons gain and lose energy traveling through the evolving gravitational potential wells of voids and superclusters. Even where gravity has left the least, its influence is readable. The universe, at every scale, is saturated with gravity's history. The structure of the web, the depths of the voids, the temperature fluctuations in ancient light, the acceleration of distant galaxies, the geometry of space itself, all of it is the accumulated record of gravity acting over 13.8 billion years, in competition and collaboration with dark energy, dark matter, radiation, and the quantum fluctuations of the earliest moment. We understand, in broad outline, how this story unfolded. We do not understand what dark energy is. We do not understand why the vacuum energy takes the value it does. We do not have a quantum theory of gravity. We are working with a framework, general relativity combined with the standard cosmological model, that is extraordinarily successful and also demonstrably incomplete. The universe has given us enough answers to build an extraordinary picture, and enough open questions to remind us, gently, that the picture is not finished. Somewhere in the gap between what we know and what we do not, between the geometric elegance of general relativity and the quantum nature of matter and energy, the deepest truth about gravity is still waiting. We have been following it for centuries. We are still following it now. We have traveled a long way together through this story. From the familiar pull that keeps your feet on the ground, through Newton's elegant inverse square law, through the profound reframing of Einstein, who told us that gravity is not a force but a geometry, that mass curves spacetime and spacetime guides mass. We have watched gravity build stars and shred them, bend light and slow time, ripple through the fabric of the universe as waves, and shape the largest structures that exist. We have arrived, now, at the edge of what is known. And the edge is closer than it might seem. For all the extraordinary success of general relativity, for all the confirmed predictions, the gravitational waves detected, the black hole imaged, the GPS signals corrected, gravity remains the only fundamental force of nature that has not been successfully incorporated into the framework of quantum mechanics. The other three forces, electromagnetism, the strong nuclear force, the weak nuclear force, have all been described, with remarkable precision, in the language of quantum field theory. Gravity stands apart, alone, resistant to the same treatment. This is not for lack of trying. For nearly a century, physicists have attempted to build a quantum theory of gravity, and the attempts have run into deep, persistent difficulties. When you try to apply the standard methods of quantum field theory to gravity, treating it as a field mediated by a particle, as electromagnetism is mediated by the photon, the mathematics produces infinities that cannot be removed by the standard renormalization techniques that work for the other forces. The theory is non-renormalizable. It breaks down. It tells you, in a mathematical sense, that it does not know how to answer the questions you are asking. The hypothetical particle that would carry the gravitational force in a quantum theory is called the graviton, a massless, spin-2 boson, whose properties can be inferred from the structure of general relativity even without a complete theory. But the graviton has never been detected, and detecting it may be beyond the reach of any conceivable experiment. The gravitational force is so extraordinarily weak that the interaction of individual gravitons with matter produces effects far below any threshold we could measure. The graviton may be real. It may be the correct description. We simply have no way, currently, to know. At very small scales, at the Planck scale, where lengths are approximately 10 to the minus 35 meters and energies are correspondingly extreme, the smooth, continuous spacetime of general relativity is expected to break down. At these scales, quantum fluctuations in the geometry of spacetime itself should become significant. Space and time, rather than forming a smooth fabric, may become something granular, foamy, fundamentally discrete, a structure so different from the spacetime we experience that our current mathematical tools may be inadequate to describe it. What happens to gravity at these scales is genuinely unknown. The Planck length is 17 orders of magnitude smaller than a proton. No particle accelerator we could build, no measurement we could make with current technology, comes close to probing it directly. Quantum gravity is not just an unsolved problem, it may be the most experimentally inaccessible problem in all of physics. But there are subtler places where quantum mechanics and gravity intersect, and some of them are within reach. Quantum vacuum fluctuations, the same zero-point energy we touched on in the context of dark energy, create a measurable effect at very small distances between objects, known as the Casimir effect, where the restriction of vacuum fluctuations between two closely spaced conducting plates produces a tiny but real attractive force. These vacuum effects complicate precision measurements of gravity at small scales, creating a background noise that must be carefully accounted for in experiments attempting to test whether gravity behaves as expected at distances of micrometers or below. So far, no deviation from the expected behavior has been found. But the experiments are difficult, and the parameter space of possible deviations is large. One of the more striking experimental results in recent years concerns antimatter. For decades, it was an open question whether antimatter, particles identical to ordinary matter except with opposite charge, falls in a gravitational field the same way ordinary matter does. General relativity predicts that it should, because gravity couples to energy and mass regardless of the sign of any other charge. But quantum field theory and cosmology raise questions about possible subtle asymmetries, and the question deserved a direct test. The Alpha-G experiment at CERN, announced in 2023, directly observed the gravitational behavior of antihydrogen, the antimatter equivalent of a hydrogen atom, and found that it falls downward, toward the Earth, at a rate consistent with ordinary matter. Antimatter does not fall upward. The equivalence principle, tested now for antimatter, holds. This is an important confirmation, but it also closes one avenue of potential strangeness, leaving the deeper mysteries intact. There is another place where gravity and quantum mechanics may interact in ways that are physically meaningful and potentially testable: quantum decoherence. Quantum systems, particles, atoms, molecules and superposition states, lose their quantum coherence when they interact with their environment. Normally, this decoherence is explained by entanglement with environmental degrees of freedom, thermal fluctuations, electromagnetic interactions, collisions with air molecules. But some physicists have proposed that gravity itself may play a role in decoherence, that the gravitational field of a particle in a superposition of two locations would itself be in a superposition, and that the energy of this gravitational superposition eventually becomes large enough to cause the quantum state to spontaneously collapse. This idea, developed in various forms by Roger Penrose and others, would mean that gravity is not merely a passive backdrop to quantum mechanics but an active participant in the emergence of classical behavior from quantum foundations. It would set a mass scale above which objects cannot maintain quantum superpositions for long, a prediction that is, in principle, testable. And experiments are being designed to test it. Several research groups are developing experiments involving small mechanical oscillators, nanoscale spheres, and carefully levitated masses, attempting to place increasingly massive objects into quantum superposition states and measure how long those superpositions survive. If gravity-induced collapse is real, there should be a characteristic decoherence time that scales with mass in a specific way. These experiments have not yet reached the required sensitivity, but they are approaching it. We may, within the coming decades, have experimental guidance on whether gravity plays a role in the quantum-to-classical transition. The strength of gravity, or more precisely, the value of the gravitational constant g, is generally assumed to be fixed, the same at all energy scales. But some theoretical frameworks predict that the effective strength of gravity changes at very high energies, just as the coupling constants of the other fundamental forces change with energy scale. In the standard model of particle physics, the electromagnetic, weak, and strong forces appear to converge towards similar strengths at very high energies, a phenomenon called gauge coupling unification, which suggests they may all be aspects of a single unified force at the Planck scale. Whether gravity joins this unification, and at what energy, depends on which theoretical framework is correct. Some versions of string theory predict that gravity becomes comparable in strength to the other forces at energies far below the Planck scale, due to the existence of extra spatial dimensions. If this were true, gravity might deviate from the inverse square law at distances of a fraction of a millimeter, a prediction that has been tested experimentally by measuring gravitational forces at sub-millimeter scales. So far, no deviation has been found. the inverse square law holds down to distances of roughly 50 micrometers. But the search continues. Some physicists have taken a different approach entirely, not trying to quantize gravity, but asking whether general relativity itself is exactly correct, or whether it needs to be modified at large scales or low accelerations. Modified gravity theories come in many forms. MOND, Modified Newtonian Dynamics, proposes that gravity behaves differently below a critical acceleration threshold, producing flat galaxy rotation curves without requiring dark matter. More sophisticated covariant extensions of MOND have been developed, attempting to reproduce the successes of general relativity while modifying the behavior at galactic scales. These theories have had some successes in predicting the detailed shapes of galaxy rotation curves, but they struggle to reproduce the full range of cosmological observations, particularly the behavior of galaxy clusters and the cosmic microwave background, without reintroducing something that looks very much like dark matter. Other modified gravity theories, are gravity, scalar tensor theories, massive gravity, alter Einstein's equations in more general ways, sometimes motivated by the dark energy problem, sometimes by theoretical considerations about consistency and completeness. None has achieved the combination of theoretical elegance and observational success that general relativity offers. But the exploration continues, driven by the recognition that our current framework cannot be the final answer. Perhaps the most philosophically striking idea in contemporary gravitational physics is entropic gravity, the proposal, developed by physicist Eric Verland, that gravity is not a fundamental force at all, but an emergent phenomenon arising from the statistical behavior of information at the microscopic level. In this picture, gravity is something like thermodynamics. Temperature, pressure, and entropy are not fundamental properties of individual atoms. They emerge from the statistical behavior of vast numbers of particles. Similarly, Verland proposes, the gravitational force might emerge from the tendency of physical systems to maximize entropy, from the way information is encoded on the surfaces bounding regions of space, from the deep relationship between geometry, information, and thermodynamics that the Bekenstein-Hawking entropy formula hints at. Entropic gravity has been developed in various directions and remains deeply controversial. Some formulations have made predictions that have been tested and found wanting. Others remain at a level of generality where clear predictions are difficult to extract. But the underlying intuition, that gravity might emerge from something deeper, just as thermodynamics emerges from statistical mechanics, resonates with a broader sense among theorists that the geometric picture of general relativity may itself be an approximation to something more fundamental, written in the language of information and quantum entanglement. The holographic principle, the idea that all the information in a volume of space can be encoded on its boundary surface, suggested by the Bekenstein-Hawking entropy formula and developed into precise mathematical form in the context of string theory, points in a similar direction. In the most well-studied holographic correspondence, a theory of gravity in a particular spacetime is exactly equivalent to a quantum field theory without gravity living on the boundary of that spacetime. Gravity, in this framework, is not primary. It is dual to something else. It emerges from the quantum entanglement structure of a lower dimensional system. What this means physically, Whether it applies to our universe, and what it implies for the nature of spacetime, remain questions at the frontier of theoretical physics, questions being actively worked on, debated, and refined. Whatever the final theory of quantum gravity turns out to be, it faces a stringent requirement: it must reproduce the predictions of general relativity in the appropriate limit. Every confirmed test of general relativity, the perihelion of Mercury, gravitational wave detection, gravitational lensing, gravitational redshift, frame dragging, the shadow of a black hole, must emerge from the deeper theory as an approximation valid at low energies and large scales. Any new framework that fails this test is ruled out, regardless of its mathematical elegance. General relativity is not a wrong theory to be discarded. It is a supremely accurate theory whose domain of validity has edges, and any successor must contain it as a special case. This is where the story of gravity stands today. A theory of extraordinary power and beauty, confirmed at every scale from micrometers to the observable universe, that nevertheless breaks down at the Planck scale, resists quantization, harbors singularities that signal its own incompleteness, and sits in unresolved tension with the quantum framework that governs everything else. Gravity is the force you have known your entire life. The one that has been with you every moment, pressing you gently but insistently toward the ground, keeping the air around you close, holding the moon in its patient arc above you. It is the most familiar thing in the universe, and the least understood of all the fundamental interactions. It built the stars you see at night. It bent the light that traveled billions of years to reach your eyes. It carved the shape of time, stretched the geometry of space, and wrote its influence into every structure that exists, from the smallest dust grain drifting in a molecular cloud to the vast cosmic filaments stretching across a universe 13 billion light-years in every direction. And at its deepest level, in the place where quantum mechanics and space-time geometry must finally be reconciled, it is still a mystery. Not the comfortable mystery of something we have not yet gotten around to studying. The deep mystery of something that has resisted the best minds in physics for a century, that breaks our best tools when we push hard enough, that keeps pointing, quietly and persistently, toward a truth we have not yet found the language to express. Gravity is the oldest story in the universe. And it is not finished yet.